Okay, so this little worksheet is a particular favorite of mine. I like it a lot. This is kind of a great, and we do some algebra with it. We're doing a lot of the rational, it's a rational function. We're doing a lot of limits. Directionally, so it kind of puts a lot of our ideas that we've been working with together. So the first thing we want to do says sketch and complete the following. Well, to sketch it, we need to factor first. So I'm going to go ahead and factor two numbers that multiply to -6 and add to -1 are -3 and +2. Two numbers that multiply to -12 and add to 1 are -3 and +4. So my x minus 3's can cancel. So that means that I'm going to have a hole here. My vertical asymptote is going to come from the bottom. My x-intercept is going to come from the top. And the relationship here was x squared over x squared. That's same degree. So my horizontal asymptote is going to come from that relationship. So let's fill in our details now. I'm going to color code here. Vertical asymptote, x plus 4 equals 0. That means you have a vertical asymptote at x equals -4. I'm going to go ahead and plot it as I go. 1, 2, 3, 4. Good start. Horizontal asymptote comes from that relationship between the top and the bottom. It was 1x squared over 1x squared, same degree. We take those leading coefficients. 1 over 1 is 1. So the horizontal asymptote at y equals 1. Our x-intercept comes from the numerator. Well, we have it canceled. X plus 2, so that means we have an x-intercept at -2, 0. That looks like it's going to fit our graph nicely. Our y-intercept is what happens when we put zeros in for all of our x's. So, when we reduce this, and for our y-intercept, we can use our reduced form. Our reduced form was x plus 2 over x plus 4. If we put zeros in there, we get 2 over 4, which is 1/2. Again, that's looking pretty nice. Our removable discontinuity is happening at where we can cancel there. So that hole was x minus 3. So it's at x equals 3 is where we have that removable discontinuity. Now we know how to find the y value, so let's go ahead and find that. To find the y value by hand, we take our reduced form, which was x plus 2 over x plus 4, and plug in that 3. So that's going to be 5 over 7. So it's x equals 3. The ordered pair is 3 5/7. We're just going to estimate that there. Our non-removable discontinuity was just that asymptote. It's a discontinuity we cannot get rid of. Okay, so this is looking good so far. I do think we need a couple more points in order to make our curve, particularly around our asymptote. We like to have a couple more points. So what I'm going to do is I'm just going to add a page in between here. See if I can do a little split screen real quick and get us a couple points. So our vertical asymptote is at -4. So I would like the value at -3, and then a couple on the other side. So let's do -5 and -6. And again, we can use our reduced form here. Our reduced form equation, that x plus 2 over x plus 4, the only difference between it and our original equation is that whole. So we can use this reduced form. So I'm going to plug -3 in. And at so -3 plus 2 is -1. -3 plus 4 is +1. So at -3, my ordered pair is -3, -1. I'm going to go ahead and plot that over here. I know that's tiny, but we'll draw it. So that is going to make a nice curve for us. Let's do 5 and 6. At -5, so on top I'm going to have -3. On bottom, -5 plus -1. So my ordered pair there is going to be -5, 3. And at -6, so -6 plus 2, -6 plus 4. And that looks pretty darn good, I think. Okay, so I'm going to go back to one screen here. We're done with our table for now, and we can draw in this curve. Feeling good about our function here. All right. That's more than a sketch there. We plotted those points. It's looking good. All right, let's see if we can evaluate the following. F of -4. So what is y when x is -4? Well, let's look. At -4, we have the asymptotes. We don't have a value. We're going to say it does not exist. At -2, our value, our output is 0. The point is -2, 0. At 0, our output was 1/2. At 3, we have the whole, so we're going to say it does not exist. So we're just using that graph to evaluate those or give those ordered pairs. All right, I'm going to snag our pretty graph here, and then we're going to do the limits. All right, now I have our graph, and I have our problems all together, so we are ready to roll here. All right, our limit as x approaches -2. So as we approach -2, this is a two-sided limit that we're looking at. So as we approach -2 from both sides, we're going to 0. As we approach 4 from the left, we're going up towards positive infinity. Oh, sorry, I just jumped to 16. I guess I can go down the column here. We'll come back to that one. Let's do 0. Our two-sided limit as we approach 0. So from both directions here, from the left and from the right, we're going to 1/2. As we approach, for number 13, as we approach 3 from the left, well, we evaluated that point. We found that at that point, our removal of discontinuity was 3 5/7. So we know from the left and from the right, we're going to 5/7. Right? The trend of our graph, if that hole wasn't there, we'd be at 5/7. And so the two-sided limit is 5/7. Now, the actual point there, f of 3, is what does not exist. So this is the reason that limits exist. The holes and asymptotes are the reasons that limits are important to us. We can't describe what's going on this graph at 3 without limits. Otherwise, it's just like, it's a hole. I don't know where it is. All right, let's go back and talk about 16 again. 16, 17, and 18 are all talking about, are all working with this asymptote. So at -4 from the left, we said we're going to positive infinity. -4 from the right, we're going to negative infinity. And so that means a two-sided limit, whether those infinities matched or not, our two-sided limit does not exist. It's not a number on a number line that I can walk to and stand on. Okay, now we're doing our end behavior limits. So now we're talking about where's our graph going at the very, very end. Our graph at positive infinity, so as we go out this way, where is our graph going? Well, our graph is trying to hit this horizontal asymptote at y=1. So our limit as we approach positive infinity is +1. And as we approach negative infinity, our limit is also +1. That is from our horizontal asymptote at y=1. All right, I really like that. That one paper is a really nice wrap-up of a lot of the things that we've worked with. It had factoring in it, canceling, asymptote, whole, one-sided limits, two-sided limits, end behavior, asymptotes, lots going on. Love it. Please let me know if you have any follow-up questions.